Guys, are you there?
Yes, sir.
Right. Cool. So let's start. Right. So if you can remember, like we were doing something regarding dipole moments, right? So I told you dipole moment is a vector, right? So when I say dipole, dipole talks about equal and opposite charges separated by a distance. So here in chemistry, how can we interpret dipole? Whenever I have polar molecules, right? Whenever I have polar bonds in specific, right? So you'll see that the electron cloud will be towards more electronegative element, thereby it will induce a partial negative, and the electron cloud is moving away from one atom, and that atom I'm going to have a partial positive, so that I'm going to have a dipole, right? And then we saw what dipole moment is. So dipole moment is going to be a vector quantity, right? And then it is equal to Q into D, where Q is the charge and D is the distance of separation. And in chemistry, the D is going to be the bond length, right? And the Q, which talks about the partial positive and partial negative charges, right? Okay. And we saw molecules, say whether they'll have some net dipole moment or not, say whether it's canceling this side and that side. If it's there, I mean, if it's canceling, it is zero. If it is not canceling, it is non-zero. And then we compared molecules which will have more dipole moment and all that, right? So all these things we did. So we'll move on. We'll continue with that, right? Okay. Right. Cool. So let me take ammonia molecule. Okay. Let me take ammonia molecule and I'll see how the dipole moment is looking here. Okay. Right. So please don't forget that there is going to be a lone pair, right, on nitrogen atom. Cool. Right. So now tell me, do I have any polar bonds here? Huh? Do I have any polar bonds here? Guys, I'm asking you a question. So I'm asking you, is there any polar bonds here? If I have, yes, if yes is your answer, and if yes, how many are there? Hello.
Yes, sir.
Very good, right? So I'm going to have 3 polar bonds, isn't it? I have 3 NH bonds. Obviously, nitrogen is more electronegative, hydrogen is less electronegative, right? So obviously, you see that there is going to be 3 polar bonds here. 3 NH bonds are there, right? Okay. Now tell me, obviously, I'm going to have some dipole moment. Obviously, we understood that. Tell me, for example, if I take this bond, right? The dipole moment of this bond will be in which direction? Towards what?
Towards nitrogen.
Towards
Yes,
nitrogen.
correct, right? So obviously, I told you the direction of dipole moment of a single bond will always point towards the more electronegative element, right? The direction of dipole moment will be in such a way that it is pointing towards the more electronegative element, right? So very simple. So I can easily say that the dipole moment is pointing towards this side, and towards this side for all these 3 bonds, right? For the 3 bonds, this is how the dipole moment is existing. Okay. Now I'm introducing to a new concept, right? Now, since you have a lone pair, right? Now that lone pair can also act as a dipole, like in the sense, right? There can be some dipole moment associated with the lone pairs also, right? And it is one of the strongest dipole moments. I would say when I compare, like say NH bonds and stuff, and if I compare with the dipole moment associated with a lone pair, that will be higher actually, right? So what I'm telling you is I have 3 bond dipoles, right? I have 3 bonds which are polar, so they will have some corresponding dipole moments. Other than that, I have one more dipole moment also, which is because of this lone pair, which is going to point towards the lone pair. That's it is going to point towards the lone pair. So apply, guys, please remember the dipole moment will either point towards more electronegative atom, or if I have any lone pairs present in the molecule, it is going to point towards the lone pair also. So there are 2 directions which you have to remember. No? 2 directions, 2 ways, like 2 categories you have to remember. One with respect to more electronegative element, and the other with respect to the lone pair. The dipole moment is going to point towards the lone pair, right? So here you have 4 dipole moments, 3 for the bonds, that is the polar bonds, NH bonds, and 1 for the lone pair. And obviously you see everything is pointing up, right? Everything is pointing up, right? So if I talk about the overall dipole moment here, right? If I talk about the overall dipole moment, can I say the overall dipole moment will be in this direction, right?
Yes,
Because
sir.
everything is pointing up, right? Everything, this is pointing up, this is pointing up, this is pointing up, and the lone pair is also pointing up, right? So the overall dipole moment here will actually be pointing totally upwards. And it is going to be a good value, good significant value of dipole moment I'm going to get for ammonia molecule. Is it understood? Say I can give you one more example. I can take the example of water. We'll see what happens there. Say in water, like this, I would have had, right? Okay. So obviously I have, again, I have 2 polar bonds. You can see OH bonds are highly polar. So for this bond, it is pointing towards this side. For this bond, it is pointing towards oxygen. And obviously I have 2 lone pairs. And we can say that it is going to be like this. It is going to be like this. All this, right? So again, obviously, I don't want to go into the resolution of this vector, but still you can see that the lone, it is pointing towards the lone pair. That's what I want to show, right? There are 4 dipole moments here. 1, 2 for your OH bonds and 2 for your lone pairs on oxygen, right? So again, I would say the overall dipole moment is actually going to point upwards, right? The overall dipole moment is going to be pointing upwards. Understood? Okay, now let me take another example. Say I want you to compare the dipole moment value. Like we don't know the exact value, but at least like tentatively we'll be able to tell for this molecule. And if I compare with NF3, right? If I compare NH3 with NF3, right? Which is going to have more dipole moment? We'll be able to guess. Can you guess?
The upper one, sir, not NF3.
Exactly, right? Now, how will I tell it? Because here you see that fluorine is more electronegative. Fluorine is more electronegative than hydrogen, sorry, nitrogen, right? So what will happen? For this bond, you will have a dipole moment pointing towards this side. For this, it is pointing towards this side. And for this, it is pointing towards this side. And obviously for lone pair, it is going to point towards the lone pair. That is done. So how many? 1, 2, 3, 4. Again, I have accounted for 4 bonds, right? Okay, so you see that one of the dipole is pointing upwards and the other 3 are pointing downwards. So there'll be some net dipole moment. Dipole moment is not 0. That is not the case here. But you can look in, if I compare this molecule and this molecule, all the 3 NH bonds are also pointing up and this lone pair is also pointing up. But in this case, 3 bond dipoles are pointing down and the lone pair is pointing up. I would say the overall dipole moment would be pointing up or no. The overall dipole moment in this case is going to point down. Why? Because you have 3 F bonds, 3 fluorine atoms, and there's only 1 lone pair, right? So I would say the overall dipole moment is going to be pointing downwards, not upwards. And even though if I talk about the magnitude will be higher here than the magnitude here. Obviously, the sign will change, right? The sign will be different for this and this. But if we talk about the magnitude, definitely magnitude of dipole moment of NH3 will be higher than that of NF3. Did you understand? Right? Okay, cool. So we'll take cases where I have lone pair, right? I have lone pair, but still you will sometimes see that the dipole moment is 0. We'll see how is that possible. Okay. Okay. I'm going to take the example of XCF4. Okay. Now, first thing what you have to do is we have to know the hybridization, we have to know the structure, we have to know the shape, geometry. Then only we can even go for dipole moment, isn't it? So I'll ask one by one. Okay. Whom should I ask? Venisha. Venisha.
Yes, sir.
Ankana,
Yes,
can you
sir.
tell me what will be the steric number here? Or if you can directly tell me what will be the hybridization also on hybridization. Okay, first.
Okay, sir.
Okay, we'll go step by step, right? So tell me,
Okay, sir.
so tell me
SP2
SP2,
D2.
SP2 D2 or SP3 D2?
SP3 D2, sir.
Okay, fine. So it's easy, right? So I have to just calculate the number of bonding atoms and the number of lone pairs, right? So Kana, here, how many bonding atoms are there, Manisha? How many side atoms are there? Manisha?
Yes, sir.
I'm asking you, how many side atoms are there in this molecule?
4.
Good, right? There are 4 fluorine atoms. Okay, very good. Right? Okay. Now, xenon has how many valence electrons? Xenon has how many valence electrons?
8.
Very good, very good. Right. So it have, because it belongs to the noble gas family, so it will have fully filled octet configuration. Very good. So it will have 8 valence electrons. Right. So 8 out of the 8 valence electrons, can I say 4 are involving in bonding with fluorine? So how many electrons are still left in the valence shell for xenon? This thing, Venisha?
4.
Very good.
4.
Right. So 4 electrons are left. So how many lone pairs? 4 electrons means how many pairs?
2.
Very good. Right. So I have 2 pairs, two lone pairs. So 4 plus 2 will become 6. Now what you told is correct. So obviously I'm going to have sp3d2 hybridization. Very good. Thank you, Vinisha. Right. Okay. Next, whom should I ask? Sashmit, are you new, Kana? Sashmit?
Yes, sir. I am
Oh, you
new, sir.
joined. Okay. Okay. Do you know about hybridization shapes and all that? Do you know?
No, sir.
Oh, fine. Anyways, you will catch up. Okay. Don't worry.
Yes, sir.
I'll ask somebody else. Mithun. Mithun? Oh, Mithun will not be able to answer. Will you be able to text Mithun? I understood. Okay, Mithun. So, Mithun, can you tell me? I have sp3d2, and this is of the form AB4L2. Correct? We just found out 4 bond pairs and 2 lone pairs. Can you tell me what will be the shape and geometry? At least the geometry. Shape, I'll ask somebody else. Can you tell me the geometry? Yeah, correct. Octahedral. Wonderful. Right. Okay, fine. Bhavadarini, are you there? So yeah, the geometry is octahedral, people, for sure. Cool. So Bhavadarini? No, not trigonal pyramidal. Whatever the answer you gave before was correct. Okay, geometry is octahedral. Correct. Spheric number 6. The moment you see that, it is octahedral or square bipyramidal, not trigonal bipyramidal. Okay.
Sir, am I
Bhavadarini,
audible? Audible,
yes,
sir?
Kana. Now only you're audible. Yes. Okay.
Okay,
So
sir.
what is the shape, Kana? Think about it. So you see that there is going to be octahedral geometry. You know how octahedral looks, right? So in the octahedral geometry, I have to put 2 lone pairs also. So hope you know where to put it, right? So I'll just imagine the shape and tell me.
Square planar, sir.
Very good, very good, very good. Yes, it is square planar. Thank you, Bhavani. Right. So I have xenon, F, 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 and F. So obviously there are 2 more bonds left. This is my octahedral shape. So here I'm going to have a lone pair. Here I'm going to have a lone pair, and I told you how to remember it. Just close this and close this. What you see is a perfect square in the same plane, right? So here the shape is actually square planar. Okay, fine. Now we asked all this just to decide what will be the dipole moment of this molecule, right? Can you guess what will be the dipole moment? Anybody?
Zero,
Can you
sir.
guess? Zero. Wonderful, right? So how can I say it? So now I have again 4 HCF bonds, right? So we know where all the 4 bonds, how the dipole moment is pointing. So obviously towards this fluorine, towards this fluorine, towards this fluorine, and towards this fluorine, right? And I have lone pairs also definitely pointing towards the lone pair. So I would have had one dipole moment here and another dipole moment here. What happened now? This is cancelled by this is cancelled by this, and the 2 lone pairs of dipole moment are also cancelling. So here mu is 0. That is, the dipole moment is 0. Everything is cancelling out each other, right? So it's not required that if I have a lone pair or if I have more than one lone pair, a dipole moment need should be, should some value. It is not necessary, right? According to the structure, if it is symmetrical, right? You can say, I told you, whenever you have a symmetrical structure, right? Whenever you have a symmetrical structure, definitely I'm going to have dipole moment to be equal to 0, unless and until all the bonding atoms are same. Say for example, here I have fluorine, here I have fluorine. Definitely I would have had some dipole moment, right? But still, in this case, dipole moment is 0. Okay, fine. So this is how we go for dipole moment, people. Like one more example also, I'll be able to give you. If I take the example of I3 minus, right? Hope you remember I3 minus. There were so much special things about it, right? So first take this down, then I'll speak. Okay, so I have I3 1 minus. So if you can remember what and all happened there, right? Okay, let me again calculate the steric number. We'll go for the geometry, then the shape, right? Okay, Shruti, can you tell me what will be the steric number here?
Sir?
Steric number, steric number. So let me give you a tell me.
4, sir.
4. There are 2 bonding atoms. Okay, there are 2 bonding atoms. How many lone pairs are you expecting?
2 lone.
Okay, now look at this. Like this might be little difficult to interpret. Okay, now let me put it like this. Okay, so I have 3 iodine atoms, right? So let me put the negative charge to the central atom. Generally, we don't do it like this. Like for this molecule, if you can remember how we did the hybridization, we looked at the Lewis dot structure, and from that I had a coordinate bond and all that, and then we decided, okay, this is going to be such hybridization, right? But directly, if I don't want to do that, how will we do it? Say put the negative charge to one of the to the central iodine atom. Okay, now the central iodine atom has, instead of 7 valence electrons, it has 8 valence electrons. Okay, let me think like that. Okay, so if I have 8 valence electrons, there are 2 more iodine atoms. So the central iodine atom will have one bond this side, another bond this side with the 2 side iodine atoms, right? So out of the 8 electrons, that is was there, that was I minus, right? So it was 8 electrons, 2 are involving in bonding. So how many lone pairs?
3 lone pairs.
That's it, right? So I have 3 lone pairs. 6 electrons are left out, so definitely 3 lone pairs. So it is 5. So sp3d hybridization. Okay, thank you, Shruti.
No, okay, sir.
Yeah, whom should I ask? Abhishek. Abhishek.
Sir,
Can you tell me what will be the geometry? I'm not asking you the shape, I'm asking you the geometry. So the moment you see steric number 5 or sp3d hybridization, what is the geometry?
sir, it's TBP, sir.
Yeah, exactly. Wonderful, right? So it is trigonal bipyramidal geometry. Thank you, Abhishek. Okay, lastly, I want to know the shape. Whom should I ask? Right? Rohan?
Yes, sir.
Yes. Can you tell me what will be the shape?
Sir.
So I have 2 bond pairs, 3 lone pairs, and I have
It will be
TBP
linear,
geometry.
sir.
Exactly. Right. So if you can remember, I have its TBP geometry will be like this: one equatorial region and another what is that, axial region, right? And there was one rule, right? There are actually 2 rules. One for more electronegative atoms should be placed in the axial position, right? Now, second thing was if I have lone pairs must be placed in the equatorial position, right? So here I have 3 lone pairs. So 1, sorry, 2, 3. These 3 are the equatorial positions. So I have 2 more iodine atoms. So done. So obviously you can see that it is linear. Okay. Thank you, Rohan. Right. Fine. Now tell me. Look at the structure and tell me whether I will have any dipole moment or not. Will it be 0 or will it be non-zero?
Non-zero, sir.
Why non-zero? It is symmetrical only, right? See, okay. So this and this are getting cancelled. There is no doubt about it.
Yes, sir.
Correct. Right. Say if I take these two, obviously towards this little point, towards this little point, towards this little point, no doubt. Right. So I can take those for the lone pairs case. I can take any 2 at a time. Right. So I take these 2 at a time. Right. So if I take these 2 at a time and I resolve this vector, can I say for these 2, you will see that the what is that? The resultant is going to be towards this side. I mean, for these 2 alone, I'm telling. Right. For these 2 alone, if I resolve the vectors, you will see that it is going this point towards this side, and this side is cancelled by that. Very simple. So you will have
So
dipole.
won't the magnitude towards the left be greater, sir? Because there are 2 lone pairs on the left and only one
That's
on the
what.
right.
Correct. I understand. But if I talk about the resultant, right? So resultant direction is this. What is
Yes,
the
sir.
resultant is magnitude. Magnitude, if you can remember, r of this will be equal to root of a squared plus b squared plus 2ab cos theta. This would have been the formula. From physics, I'm telling. From the the
Yes, sir.
magnitude of resultant vector. If you calculate this, say now both are same, right? Say I'll call it as both are same, right? Both A and A are what is there. The values are same here because it's same lone pair. Correct. So you will see that if I calculate it, I don't know what is cos theta. Cos theta is 120 degrees. Cos is 120, right? Here the angle is, it will not be exactly 120, but still fine. So if I write it like this, I have a squared plus a squared. So it is 2a squared plus 2a squared. Cos theta, I'll keep it as 1. Okay, cos theta, I'll
Yes,
keep it as
sir.
1. Okay, so now if I bring this in the root, so you'll have root of 4a squared. So what will you get? 2a. Oh. 2a squared cos theta. Now, instead of maybe I'm doing something wrong, maybe cos theta maybe plays a role, right? Or what I can do is if I take my BF3 molecule, right? If I took my BF3 molecule, which is only trigonal planar, right? So in this case, obviously, I told you that again, same thing will happen. Same thing would have happened. Since it is symmetrical again, 120, 120, 120, I told you that mu was 0 here. Correct. So same thing can be understood here also.
Okay.
Everything
Okay,
is
sir, yeah.
symmetrical, right? So again, I
Yes,
can
sir.
say that the lone pair, this thing is 0. See, if at all, the telling that you are saying that this side only 1 is there, this side is there, but actually, if you see, it's in the same plane. For example, it is something like this. I don't know how to show you. One second. I don't know whether you're able to see. No, this is not working. Anyways, so the thing is it's symmetrical. Okay, so 120, 120, 120, all the bond angles are same. If at all say one of them was 120, another was 90, then what you're telling might be is correct, right? But
Okay,
both
sir.
are all equal magnitude and symmetrically placed, so 0,
Understood, sir.
right? Cool. So guys, that's about dipole moment, right? So they might even ask the questions like this: which of the molecules are polar, right? If they ask you like this, you have to calculate the overall dipole moment, and if you find that the overall dipole moment is not 0, then those kind of molecules are what are called as polar molecules. There's a difference between polar bonds and polar molecules. Polar bonds, the bond, like the atoms involved in the bond should have some electronegativity difference. If I say polar molecule, that should definitely have some net dipole moment. It should not be 0. Okay, right? So we'll move on to the next concept. What is cos 120 degrees? Cos of 120, I can write it as cos of 90 plus 30. Correct. So it is cos of 90 plus theta. So it is all silver teacups. So 90 plus theta. So only sign is there. So minus, cos is negative, and 90 plus theta will become, so 90 whenever I have it is going to be minus of sine 30. So it is minus 1 by 2. Okay. Even by the calculation it will work, Anna. Rohan?
Yes, sir.
Right? Even by the calculation, same thing will have. I'll have 1 by 2 also there. So it'll get cancelled.
Yes, sir.
It'll
It'll
get root of
be
a.
yes, sir.
Correct, a squared. And root of a, it'll be, in a squared will be a. Right. Okay, cancel it. Right, cool. So next concept we are going to see. Okay, so now I'm going to tell you something weird. Okay, so we know that we have ionic compounds, right? So we say that I have a proper cation, anion is there. They have very strong force of attraction. All those are there. But the thing is, no ionic compound is 100% ionic. Or I can even say that in case if I have certain covalent compounds, right? So even those covalent compounds are actually not 100% covalent. Not all of them. There are covalent compounds which are 100% covalent, right? But still there are covalent compounds which will have some ionic character, right? And again, speaking in terms of ionic compounds, now at least in case of some covalent compounds, they were 100% covalent. But here in an ionic compound, no ionic compound is basically going to be 100% ionic. Okay. Now, why? How will I say this? How am I going to prove it? All this we'll see, right? But till now, we have been speaking about it, isn't it? We say that ionic bonds are there, ionic compounds, ionic bonds, all these things we were saying. What does that mean then? If at all they are not actually going to be 100% ionic, but still, why do we call them as ionic? Is because which character dominates is the question there. If at all you see that so obviously you can have 50-50% chances, ionic character 50% and your covalent character 50%. So obviously whichever is higher in number, say for example in a molecule you see that it is 70% ionic and 30% covalent, I will call the overall molecule as ionic only, right? Or like again, say if it is 50-50, then again it depends, right? Whether I'll call it as an ionic compound or a covalent compound depends, right? So but again, if it is more than 50%, if the ionic character is more than 50%, then only I'll be calling it as an ionic compound. Okay. So the question is, sir, how is it that a covalent character is coming into the picture of an ionic compound? Is the first question you'll ask me, right? So we will look into it, right? So we are looking into, okay, before that, right? So I told you that in covalent compounds also I can have ionic character. That I told you, right? So let me take some examples for that. It's very easy to understand. We have already studied it. So obviously, whenever I have polar bonds, what do you see? Say, for example, if I have HF bond, what do you see? You see that there is a del negative, there is a del positive, right? So even though they are not absolute full charges, but still you see there's a cation kind of thing, there's an anion kind of thing. So whenever you have polar compounds or polar bonds, they will have some ionic character. So that's what happens in your covalent compounds. Very simple, right? So I would say whenever covalent molecules have polar bonds, so they will have some ionic character. That is very simple because I have partial positive and partial negative. Not full ionic the character, but still some ionic character. Some ionic character will always be there if the molecule is having a polar bond. Say, but if I have H2 molecule, no, definitely it will not have any ionic character. Right? So yeah, so this is very easy, right? Ionic character in covalent compounds is little easy to understand. Okay, now we'll go for the opposite. Covalent character in ionic compound. That's what is our concept today, and that is what is more important also. So see that. So this you can take down whenever you have a covalent compound, and if that covalent compound has polar bonds, I will have some ionic character because I have a development of partial positive and partial negative charges. Okay, fine. I will move on. So I'm talking about covalent character in ionic compounds. Okay, right. Cool. So first you have to understand how covalent character comes into the picture. Then we can actually compare. Right? If I give you 2-3 molecules, we'll be able to compare which will have higher ionic character, which will have higher covalent character. All these things we'll be able to predict. Right. But anyways, so we'll talk about this. So generally, I know I'm going to have a cation, right? And generally, cations are smaller in size when compared to anions. That we already know, right? When I compare the parent atom with the size of the parent atom with the cation, parent atom will have higher size, right? But if I go for anions, when I compare the anionic size with the atomic size, anionic size is bigger. Right? Anyways, we have studied this in what is that? Periodic table. Right? Anyway, so I'm going in an ionic compound. This is an ionic compound where I have a cation and an anion. No problem. Right? Now this is 100% ionic. Okay. Right. But what exactly is going to happen is, now since there's a positive charge which is having a deficit of electrons, isn't it? Positive charge, I know how is it formed. It is losing electron to make a very strong positive charge. Okay. Right. And I know anions are going to have very large number of electrons. They are electron rich, right? I know anions are electron rich, and my cations are electron deficient. Is it not? Or I would say that positive charges are going to have a natural attraction towards the negative charges. Negative charges means electrons which are there in the anion. Okay. So now what is going to happen is, so since they're very close enough, I know cation and the anion will be little close enough. So what is going to happen is, say I am going to have an electron here, right? Or I'm going to have an electron here. So if at all there was no interaction between this cation and this electron, it will be perfectly ionic. There will not be any interaction, right? But since it is electron deficient and this is electron rich, what is going to happen is, the electron cloud of your anion, that is the cloud of the anion, is going to get distorted, right? How distorted, I'll be able to tell you. So if it is a perfect square, perfect sphere, right? So what happens is, because I have some attraction here, I am going to have a distorted field like this, right? This electron which is here is actually moving towards the cation. Right? So I would say it is not going to be a perfect sphere. It is going to be, something like this. The anions, electron cloud would have gotten distorted. Right? Electrons, the anions, this is my anion. Right? The anions electron cloud is little distorted because of the presence of the cation. Right? So can you see that there is something like a mutual sharing coming into the picture here? Right? Is it not? If it is a perfectly sphere, it is a perfectly ionic compound. But since the electron cloud is little moving towards your cation, I would say it is not fully shared. If it's a fully shared compound, yes, it's a perfectly covalent compound. But it is not fully shared It is not an ionic compound because it is the electron, the valence electron of the anion is moving towards the cation like this. Okay, so I'm going to have a distortion of the electron cloud around the anion. Okay, so this is what is bringing the covalent character into ionic compound. So this will happen for any ionic compound, isn't it? Because everything will have cation, everything will have anions, and anions will have valence electrons, and cations will attract the electrons. So obviously there is going to be some kind of distortion of electron cloud happening in all the ionic compound. Now the question is where it will happen more, where it will happen less is the question. So obviously if the distortion happening is less, then I say that ionic character is Y, covalent character is more. Correct, right? So please understand this distortion of the electron cloud is the reason for covalent character in ionic compounds. Okay. Now I'm going to give you some technical terms, right? So this entire phenomena, whatever is happening here, the distortion of electron cloud of anion because of the cation, this entire phenomena is what is called as polarization. Right? This entire phenomena is what is called as polarization. So if at all I want to give you a proper definition of what polarization is, right? Polarization, you can take it down if you want. Take it down. Right. So yeah, so polarization is the phenomenon of distortion, DIS, distortion of electron cloud. Polarization is the phenomenon of distortion of the electron cloud of anion by cation. Anion is the one for which it is happening, electron cloud is being distorted, and cation is the one that is causing it, right? So polarization is the phenomenon of distortion of the electron cloud of anion by cation. Very simple words, we defined it. Okay, now two more technical terms. One is there are three technical terms. First is polarization, we understood that. Second thing is I am going to give a technical term for anion, and I'm going to give a technical term for cations also, right? So there was a very good example, right? Say if at all there is a politician who speaks, okay, he was speaking in a stage, right? So if at all he speaks very well, right, and all the people are actually falling for whatever he's saying, right? So I would say that the politician is actually polarizing the crowd. Maybe it's a little big of an ask, but still, right? Basically, or we're not going into all that. So please understand that cation is the one who is polarizing, right? And your anion is the one which is getting polarized. Hope you understand the difference, right? Distortion of electron cloud is happening for anion. By who? By the cation. So I would say that anions are getting polarized. They are getting polarized, right? And the cation is polarizing the anion, right? I would say they are getting polarized. That is, anions are getting polarized because of the cation, and cation is polarizing the anion. Like, hope you understand what I'm trying to tell, right? Who's doing what? Anion is getting polarized, and who's doing that? Cation is polarizing the anion. Very simple to understand. Okay, now I would say the covalent character, right? The covalent character will be more and more and more if more and more and more polarization happens. So I'll be able to put it in a nutshell and tell that covalent character is directly proportional to the amount of polarization which happens in the ionic compound. That's very simple to say that, isn't it? Covalent character is going to be directly proportional to the amount of polarization which happens in the ionic compound, right? So obviously it is going to depend on whether the anion is getting polarized right? And it is also going to depend upon whether the cation is capable of polarizing the anion, isn't it? So this capability of the anion, I would say this capability of the cation to polarize anion, this entire term, this entire thing is what is called as polarizing power of cation, right? So you can understand that the cation is the one which is polarizing the anion. So for cation, how will I speak in terms of polarization? For cation, I'll speak in terms of polarizing power. What is polarizing power? It is very simple. It is the capability of the cation to polarize the anion. It is how much ability it has to cause the distortion, right? That is what is called as polarizing power, isn't it? So I can also give you one more statement. The covalent character, I call it as CC, right? So the covalent character, can I say, will be directly proportional to the polarizing power of the cation. I say first statement what I gave is covalent character is directly proportional to the amount of polarization. The amount of polarization will be higher if I have high polarizing power of cation. Obviously, the covalent character will be directly proportional to the polarizing power of the cation. Okay, now if I speak in terms of anion, anion is getting polarized. So again, I'll give you one more definition for anions. So the ability of anion to get polarized, right? Ability of the anion to get polarized, that particular term is what is called as polarizability. What is polarizability? Polarizability, it is the ability of the anion to get polarized. That means the ability of the anion to get this electron cloud distorted. Okay, so obviously if the ability of the anion to get polarized is higher, or I would say if the polarizability of the anion is higher, obviously the amount of polarization which is happening is higher. So definitely CC, that is the covalent character in an ionic compound, is again going to be directly proportional to the polarizability of the anion. Okay, so guys, did you find any doubts here? You can ask me now because we're going to continue. Is it okay? Everybody understood?
Yes.
Yes, sir.
Okay, fine. So we have to remember only two terms. One is polarizing power of the cation, other one is polarizability of the anion. And both the cases, the covalent character in a molecule is directly proportional to both of them. What is polarizing power? Ability of the cation to polarize the anion. What is polarizability? Ability of the anion to get polarized. Very, very simple terms, right? Next, what you're going to see is how I will be able to compare the polarizing power of two cations, or I'll say how will I be able to compare the polarizability of two anions. All these things we'll see now. Okay, fine. So we'll move on. Okay, fine. Cool. Now let me see first logically, right? And then there is actually some rules which will be able to help you with. But again, if I know the logic, the rules, everything is going to be same. Okay, fine. Now first we'll talk about the polarizing power of the cations. First we'll talk about the cations, right? So we are talking about the polarizing power. Okay. Now, can I say that so all the things are happening just because the cations are attracting the valence electrons of the anion. That is why this is all happening, right? So obviously, if I talk about the cations, if the cations are very heavily charged, basically if I have very high amount of positive charge on that particular cation, can I say it will have very stronger attraction for the anions as electrons? Isn't it? Right? So I'm talking about the amount of charge. Say for example, if I compare Na plus and Mg2 plus, for example, right? So obviously Mg2 plus is having more positive charge than Na plus, isn't it? So obviously Mg2 plus will have more capability to pull the electron of the anion towards itself. Or in other words, Mg2 plus, since it is having more positive charge, will have more polarizing power. Is it not? Because it is having more positive charge, so it will be able to attract the electrons towards itself and in a little more stronger way than in the case of Na. Isn't it? Right? So that's the first point. Or actually, I'll be able to see it in the terms of, okay, we'll actually combine the logic as well as the rule, which I'm going to see. So the rule is what is called as Fajon's rule. F-A-J-A-N-S. Fajon's rule. The Fajon's rule basically talks about, again, how to compare two or more molecules for their ionic character or covalent character. Okay. So anyways, we'll see what is this. Don't worry. So first, what I'm also talking about cations is polarizing power. I'm speaking. So what I told you, the first point was the more and more charge, the more and more positive charge that particular that a cation has, more and more will be the polarizing power. More and more will be the ability of the cation to attract the electrons. Right. So first, for Fajon's rule, I'll be able to say this. If I talk about cations, we're talking about cations, right? So first is the charge present on the cation, right? So obviously that present is directly proportional to the polarizing power, right? And that in turn I know is directly proportional to the covalent character, right? Say for example, if I compare NaCl, NgCl2 and AlCl3, right? I want to know which is maximum ionic or which is maximum covalent or whatever it is, right? So in this case, you don't have to worry about the anions because all the anions are same here, Cl, right? The only thing which is varying is about the cations. Obviously, I know here I have +3 as the charge for aluminum, +2 is the charge for magnesium, and +1 is the charge for sodium. Correct. Now, what did I tell you? More and more charge present on the cation, more and more will be the polarizing power, and I gave you the reason also. And obviously, that is going to be directly proportional to the covalent character. So obviously, in this case, when I compare the covalent character, AlCl3 is more covalent than MgCl2, and MgCl2 is more covalent than NaCl. So I would say if we talk about the ionic character, NaCl would have been the most ionic, AlCl3 would have been the least ionic. So this particular thing is for the covalent character. Okay, right. So that is one of the criteria for your cations. That is the charge. Okay. Now next thing is about in the cations itself. One is charge. The other one is size of the cation. Okay. The other one is size of the cation. Right. Okay. Now how will I be able to prove this to you? Right. So please understand, people. Okay. Let me compare. LiCl, NaCl, and KCl. Basically, I have Na plus, and Li plus, Na plus, and K plus. All of them are having same charge now, +1 charge, right? So in this case, how will you go about it? So I can easily again go for the logic here, right? Say okay, so I have a very small cation and a big anion and a little bigger cation and a little same size of anion. Okay, fine. Now think and tell me, I have a small positive charge and I have a very big positive charge, in which case will have more attraction for electrons?
The larger one, sir.
Okay, right. So this is what we think, right? But the thing is, you have to speak in terms of charge density. Right, wherever the amount of charge density is higher, right, wherever the amount of charge density is higher, that will have more amount of attraction for the electrons. That means a small, what do you mean by charge density? Charge density is nothing but charge divided by size. Oh, correct. Higher the size, smaller. Correct. Okay. So please understand that charge density is equal to the charge of the particular thing by the size, right? So if I have a very small cation, having a very large amount of positive charge, will have more. Basically, how do I put it? I'm thinking of a real life situation for me to explain this. See, both of them are having +1 and +1. Okay, both of them are having +1 and +1. But the smaller cation is having more charge density. Like even though they have +1 and +1, say that positive charge is little bit easily say dispersed in the bigger area of this bigger cation. But the same positive charge +1, right, it's very concised in a very small portion. So definitely this is more unstable. Unstable in the sense it is going to have more attraction for the anions electron. Okay, so please understand that whenever size is increasing, or whenever, like in this case, whenever size is increasing or whenever size is decreasing, so you can see here what is going to happen. Charge density, if I speak here, right, both LiCl, NaCl, I mean Li plus, Na plus, and K plus are having same charge +1, right? But if I talk about the size, right, K plus is having maximum size, Li plus is having minimum size. Right, so which will have maximum charge density? Maximum charge density will be for lithium, maximum, then sodium, then potassium. I'm talking about the charge density here, right? So obviously more and more charge density, right? More and more will be the polarizing power, and obviously more and more would have been the covalent character, right? So anyways, we'll not confuse ourselves with all this. Just understand this. When I have size is inversely proportional to the polarizing power, right? Size is, you can understand here what happened. Li is having the maximum charge density, so maximum covalent character, I mean, or maximum polarizing power. So size is the least for it, right? Anyways, do not confuse. Whenever I have charge for cations, we're speaking only about cations. For cations, charge and covalent character are directly related, and for size and covalent character are inversely related, because I know polarizing power and covalent character are directly related, right? So size and the covalent character of cations are inversely related. So now if I have to compare this Li plus, Na plus, K plus, which is going to have maximum covalent character, whichever is going to have the least size is going to have the maximum covalent character. So in this case, LiCl is more covalent than NaCl, and NaCl is more covalent than KCl. Okay, so charge directly proportional, size inversely proportional. That's it. Okay, this alone you understand. And if at all you want to know why this size comes into the picture, the answer lies in charge density. Okay, more and more charge density, more and more will be the polarizing power. Okay, obviously smaller cations will have more charge density than bigger cations. That's the way to put it. Okay, so that's about the cations now. We spoke about the cations. That is, we talk about only the polarizing power, right? So what I have to speak about yet is about the anions' polarizability. Cool, right? We'll speak about it now. Right. So we are going for anions. Again, Fajon's rule only. This again comes under Fajon's rule only. Anions' polarizability. Right. Okay. So again, there are going to be two factors here. The first one is going to be the charge. Right. So obviously, more and more is the charge, more and more is the number of electrons present. Okay, we're talking about negative charge here, isn't it? So more and more negative charge, that means more and more electrons would have gotten added to this particular atom to form an anion. So more and more electrons, more and more attraction would be there with the cation. Easy, right? So again, charge is directly proportional to the polarizability, right? And I know polarizability is directly proportional to the covalent character. So definitely charge, again in this case, charge and covalent character are directly related. For example, I have NaCl, Na2O, and Na3N. But this compound doesn't exist, but still, no problem. Right. Okay, so now all the cations are same, right? Only the anions are varying. What are the anions here? Cl minus, O2 minus and N3 minus. Isn't it? Now, what did I tell you? More charge, more covalent character. Obviously, N has -3, oxygen has -2, Cl has -1 only. So, definitely, Na3N will be more covalent than Na2O, which will be more covalent than NaCl. Right? So, this is about the order of covalent character again. Understood? Right? So, that's about the charge. Charge on the anion, like magnitude of charge. Obviously, don't tell -3 is lesser than -2. I'm talking about the magnitude of the charge. Right? So, more and more is the magnitude of charge, more and more is the covalent character. That we understood. Right? Again, the reason is very simple. More and more is the amount of negative charge, more and more will be the amount of electrons and can easily get attracted towards the cation and thereby distorting the electron cloud of the anion. Okay, cool. So that's about the charge. Next one is about the size. Okay, now this can be easily understood if I talk about this. Say I have one cation and I have an anion. Again, the same cation, but a big anion. Right. Now tell me, which will have more polarizability, bigger anion or the smaller anion? Which can easily distort, where I can easily distort the cloud? Bigger one or the smaller one?
Bigger one, sir.
Definitely, right? Because you can see that if this is the valence electron in this case and this is the valence electron in this case, right? So both the valence electrons are actually having a force of attraction within its nucleus. So each nucleus will have an attraction here and this nucleus will have an attraction here, right? So if at all this electron has to get attracted by the cation, right? So obviously if the electron is little far away from the nucleus, it is definitely going to have lesser nuclear force of attraction and thereby this electron can easily get shared with the cation. Or I would say the electron cloud can be easily distorted by the cation. So bigger anions can get easily distorted. Smaller anions, it's difficult because the electron in there are having more force of attraction with the nucleus. Very simple, right? So in this case, size is directly proportional to the polarizability. Right? Bigger anions will get easily distorted, right? So definitely polarizability and the covalent character are same, directly related. So definitely size of the anions is directly proportional to the covalent character, right? So again, if I take an example, if I have NaCl or NaS, NaCl, NaBr, and Na, all are halogens. Again, all the cations are same, only the anions are varying. And all the anions are having -1 charge, like F minus, Cl minus, Br minus, I minus, all these are having -1. So again, if someone asks you, arrange them in the order of covalent character, right? So obviously I know bigger anions will have high polarizability and high covalent character. And obviously I know down the group size increases. So I minus is the having maximum size, that will have maximum polarizability. So obviously NaI will have more covalent character than NaBr, and then NaBr will have more covalent character than NaCl, and NaCl will have more covalent character than NaF. Okay, so only 4 points you have to remember, people. Like, I don't even want you to mug up. It's all logically explained. If you understand what is polarization, if you understand what is polarizing power, and if you understand what is polarizability, all these things are very much in your hands. You don't have to mug up. Okay, cations means charge and covalent character are inversely related. No, that is not how you do it. Okay, please understand the logics, and thereby it is going to be very easy. How much you will remember in the mind, how much you will mug up, how much will you remember the formulas, it is not going to help. But if you remember the logic, even though I forget it, it is going to help me, right? Okay, so anyways, 4 points you have to remember. When I talk about the cations, charge and the covalent character are directly related. And if I talk about the size and covalent character are inversely related for cations. Now, if I go for anions, I saw that charge again is directly related to the covalent character, but size is directly related. And all these has some logical reasons behind them, right? So please go through it. Like if at all you didn't understand anything before, you can again watch the video. You have that option also, right? And especially for this particular chapter, not only for this concept, this entire chapter, I would really advise you to watch the videos again, right? Even though if you find it might be boring, but still, you can just fast forward it at least and you can watch it. Okay, do something about it. Cool. So that is how I am going to have covalent character in ionic compounds. So whatever the statement I said, no ionic compound is 100% ionic. I have proved it here. And the reason behind it is polarization. Guys, any doubts? Everything is understood.
Yes, sir.
Okay, fine. Still then, so like I think we were talking about this last theory, but still we were coming up with concepts and concepts. But don't worry, all the concepts are over. Next class, we'll be talking about the next and last theory, that is molecular orbital theory. Again, the most interesting of them all. Okay, so till then, people, thank you. We'll see you again. Right?
Thank
Day
you,
after
sir.
tomorrow.
Thank you, sir.
Thank you.